Hello everyone, welcome to our YouTube channel Electronics Maddie. In this video, we are going to talk about Norton's theorem, the theory behind Norton's theorem, and few of the solved examples with respect to Norton's theorem. So let's get started. Norton's theorem. So any theorem for that matter will basically have a statement. I'm not going to read the statement as it is, but I'm going to give you an example and try to correlate what the statement is all about. So let us consider this as a typical example. You have a network and you have a load. Let us say this is our transmission and distribution network, and this is our domestic appliances load. That is nothing but the end consumers. So if they have asked us to find the current flowing through RL in this case, so we'll be able to find it using KVL or KCL or applying suitable type of analysis in solving this network. But what if the load keeps on changing? If in case of a domestic appliances or domestic application, the load keeps on changing and the current also keeps on changing. And in these cases, applying KVL and KCL and finding it out in each and every iteration, the number of iterations will increase. Instead of that, how about having an equivalent network where you represent a current source in parallel with a resistor and and then find the current IL by applying current division rule, because you know the source current IL. So this ISC. So this totally reduce the number of steps and iterations in solving a particular problem with respect to the current flowing through the load due to the changes in the load. So as a result, it saves a lot of efforts in order to do the computations involved. So isn't this helpful in this way? So let us try to look at the statement and what it states like. Any two terminals of a network can be replaced by an equivalent current source and an equivalent parallel resistance. So any two terminal network can be represented in a equivalent form by having a current source in parallel with a resistor. The constant current source is equal to the current which would flow in a short circuit placed across the terminals. So if suppose they've asked us to find the current flowing through the load, we will be short circuiting the load terminals. That is what it is trying to say. So the parallel resistance is the resistance of the network when viewed from these open circuit terminals. When we are finding out the resistance, we'll be open circuiting the load terminals in that case. After all, voltages and current sources have been removed and replaced by their internal resistances. So what does this statement mean? The voltage source or current source can be represented by their internal resistances. That is nothing but current source will be represented by their open circuit while calculating the resistance Rn, and voltage source will be represented by short circuit. So why is it actually with respect to the current source being open circuited and voltage source being short circuited? The reason is very simple. The internal resistance offered by a practical voltage source is very less, of the order of few ohms. So in ideal conditions, we can assume it to be zero. So it's assumed to be a short circuit. And in case of a current source, the ideal resistance offered by current source is infinity, the internal resistance with it. So we'll be representing it with an open circuit. So once we are clearly aware of understanding what the statement is and why it's actually used, let us try to understand the steps behind solving this network to get this particular Norton's equivalent circuit. So this is called as Norton's equivalent circuit. So how do we arrive from this point to this point? That is a big question, isn't it? So let's go into our next concept, that is nothing but the steps involved in Norton's theorem. So let us say they've given us a network in this case. So what are the steps that we have to do? And they've asked us to find the current flowing through RL. So that is IL. So remove the load resistor and put short circuit across the terminals. So we'll be removing the load resistor and we'll be shorting it. With respect to Thevenin's theorem, we used to open circuit in and find the value of VTH. But here we are actually shorting it and finding the value of the current flowing through the short circuit terminal, that is nothing but IN. So the IN is current flowing through this particular network through the short circuit terminal. Find the short circuit current, ISC or IN in this case. So second step is to find the Norton current. So once that is done, we'll be finding the resistance RN from the point AB by open circuiting it, and we'll be finding this step is similar to both Norton's theorem and Thevenin's theorem. We'll be finding the equivalent resistance with respect to the terminal by open circuiting it. Only thing is the designation with respect to Thevenin's theorem is RTH, and with respect to Norton's theorem it is RN. So once this is done, we will replace the network by a current source IN connected in parallel with RN. So we have found out IN, we have found out RN. So we can simply represent them in this form according to the statement of Norton's theorem, isn't it? So once that is done, we can find the value of current flowing through RN using current division rule. That is IL is equal to IN into RN by RN plus RL. So the current flowing through this branch can be determined by the main current that is flowing into the resistance of opposite opposite branch, that is Rn, by the sum of the resistance that is there in parallel with respect to each other. So these are the steps that are involved. These are standard steps that will be followed throughout all the problems that we are solving. So let's start applying these steps by solving few of the worked examples with respect to Norton's theorem. So our first problem is to find the value of find the Norton equivalent between points A and B. So let us say they've given this circuit and they've asked us to find the equivalent circuit in Norton's form. So what is Norton's equivalent circuit? We already saw in our previous slides. So we will be arriving at that point. So in order to arrive at that point, we need to find the value of IN, we need to find the value of RN. So once that is done, we can equivalently represent them, isn't it? So our first step is to calculate the value of IN. How do we do that? By short circuiting the terminals AB. So 2 ohm resistor will be replaced by a short circuit, and we will be finding the value of IN by applying KVL in this case. So I'll be considering the direction of current in clockwise direction. I've considered it to be uniform throughout the meshes that are there. So there are two meshes or two loops in this case. And now we will be starting by applying KVL to mesh 1. So in this case, with respect to mesh 1, you have plus 10 volt because the current is entering with respect to 10 volt, that is minus 2 plus. When it is leaving, it is at plus terminal, so we'll be writing it as plus 10 volt. So again, with respect to 1 ohm resistor, it is entering at plus and it is leaving at minus, so we'll be writing it as minus 1 into I1. Again, with respect to 1 ohm resistor, we'll be designating this as plus and this as minus, while leaving it is at minus terminal, so minus 1 into I1 minus I2, because we are applying with respect to loop 1 and I2 is in the opposite direction. Since I2 is also flowing in this resistor, we have to consider that. So I'll be representing it as I1 minus I2, that is equal to 0. This is because the algebraic sum of EMFs in a closed loop is equal to 0 according to KVL. So again, I'll try to simplify this by applying like simple mathematics by addition and subtraction of these. We will be getting this particular equation. We will be labeling this as equation 1. Now applying KVL to mesh 2. This is with respect to mesh 2. I'll do the same procedure with respect to it. Now let us say with respect to 1 ohm resistor, plus it's entering at plus and leaving it at minus. So minus 1 into I2 minus I1. Then again with respect to 1 ohm, it is plus here and minus here. You'll be having minus 1 into I2, that is equal to 0. No no elements or no components is present in this particular branch. So we'll be writing it that way. So we'll be simplifying this and labeling this as equation 2. Solving equation 1 and 2, we will be getting the value of I1 and I2. Now in this mesh, it is nothing, it indicates clearly that the value of current I2 that is flowing is the Norton's current IN. So we can write it as I2 is equal to IN, that is nothing but 3.33 amps. So once this concept is clear, like if you have any doubts with respect to applying KVL, please do refer to our previous examples that are solved with respect to KVL and KCL. A simplified analysis and each and every step is indicated in detail in that video. I'll be showing that sharing that video in the description provided below in this particular video. So step 2 is to calculate the value of Rn. So how do we do that? We'll be replacing voltage source by short circuit and current source by open circuit. That is according to our analogy that is there. So we will be looking at this particular point because they've asked us to find with respect to 2 ohm resistor, which was earlier in this place. So looking at this, 1 ohm and 1 ohm resistor are connected in parallel. So you'll be getting 0.5 when you simplify this, and that effective combination will be in series with 1 ohm. You'll be getting 1.5 ohm as a whole. Step 3 is to represent Norton's equivalent circuit according to our equation. We have the value of IN, we have the value of RN. We'll simply represent a current source in parallel with a resistor RN, and that is connected between a load resistor 2 ohm. That is all they've asked. They've not asked us to find out the current with respect to this particular network or something like that. So we'll be stopping at this point since they've only asked us the Norton's equivalent circuit. I hope this problem is cleared. We'll go into our next example. So in this case, they've asked us to find the value of current flowing through 10 ohm resistor. This is the 10 ohm resistor. Not necessary the like if you observe the circuit, usually the load resistor will come at the end, but they might ask you the current flowing through any of the branches as well at the point. So in this case, they have asked us to find the current flowing through 10 ohm resistor. So first step is to calculate the value of IN. How do we do that? Replacing the 10 ohm resistor by a short circuit. We will be arriving at this point. So now I've indicated the directions and the plus and negative signs with respect to each of the components that are there. So according to our convention, we'll be applying applying KVL to mesh 1. So with respect to mesh 1, if you see, it is entering at minus and leaving at positive, so we'll write plus 2 volt, and again it is entering at plus and leaving at minus, so we'll be writing minus 1 into I1, that is equal to 0, because there are no branch elements in this, that is with respect to point AB, because it is a short circuit. Now I will be getting the value of I1, that is equal to 2 amps. Now if you carefully observe, mesh 2 and mesh 3 basically has a current source in between. So if there is a current source in between two loops, then the concept of super mesh will take place. So we have to be very careful in observing each and every loops. So in this case it's very clear that there is a current source in between them, and we will consider this as a super mesh. If you are not clearly aware of what super mesh is all about, please do refer to our video that is discussed previously, and I'll be sharing the link as well. So with respect to super mesh, the current flowing with respect applying the super mesh concept, you will be getting writing current equation for the super mesh. So with respect to 4 amps, we can write it as I3 minus I2 is equal to 4. The reason why I3 minus I2 is written, because I3 is in the direction in which the current of 4, the current 4 amps is in the same direction. So that's why we'll be writing I3 minus I2, that is equal to 4. We'll be labeling this as equation 1. Again, I'll be applying KVL to the super mesh. Super mesh is nothing but the outermost loop when you're applying KVL with respect to it. So applying KVL to the outermost loop, we'll be getting this, that is nothing but minus 5 times I2, because I2 is the current flowing through this. So minus 5 times I2, because it is living at minus terminal. Again, with respect to 15 ohm, it is entering at 15 ohm and living at minus. So we'll be writing minus 15 I3, because I3 is the current flowing through resistor 15 ohms. So we'll be labeling this as equation 2. Solving equation 1 and 2, you will be getting the value of I1. I1 is already known. You will be getting the value of I2 and I3. So I2 in this case is given as minus 3 ohm, minus 3 amps. So the reason why we have found out only I2 here is because we need the value of IN. IN is given by I1 minus I2. So mainly we needed the current of I1 and I2 to solve and find the value of IN. So we won't concentrate on with respect to I3, but because we don't need them actually. So IN is equal to I1 minus I2. Reason why it's I1 minus I2, because IN is in the direction of the direction in which I1 is flowing. So we'll be substituting and solving, we'll be getting 5 amps. So once we have found out the value of IN, our next step is, as usual, we'll be finding the value of Rn, that is replaced by a voltage source by short circuit and current source by open circuit. So you'll be arriving at this point. This will be the equivalent representation of the circuit. From this point, it's very clear that if you carefully observe, the resistor 1 ohm is in parallel with the series combination of 5 ohm and 15 ohm. That is 5 plus 15 will give you 20. 20 ohm is in parallel with 1 ohm, because they're connected between the same 2 points, that is across AB. So we'll be finding the value of Rn. You'll be getting it as to be 0.95 ohms. So once that is done, our step 3 is to calculate the value of IL. So how do we do that? We'll represent it in Norton's equivalent form. That is the first step. We have found out the value of IN, we know the value of RN, and we'll be representing the Thevenin, will be representing the Norton's equivalent resistance, that is supposed to be with respect to the load that is supposed to be calculated. So that is nothing but 10 ohm in this case. So we'll be applying current division rule. How do we find IL? IL is found out by this formula, that is by using current division rule. 5 is the actual value of main current that is flowing in this particular circuit into the resistance value, that is the resistance of the opposite branch. So resistance of the opposite branch with respect to 10 ohms here is 0.95. I'll be writing that, and divided by the sum of each of these resistance values. So you'll be getting 0.43 amps. So once this is done, this is our approach in order to determine the load current. Now if suppose they have asked us to find out the current flowing through 5 ohms, again we'll replace this 10 ohms by 5 ohms, and we'll be calculating the value of 5 ohms with respect to 5 ohms. So this is as simple as it looks like, because it simplifies the entire process of calculating currents with respect to the loads that are there. So I guess this problem is understood. Once we are clear with this, let's go into our next problem. This problem is slightly tricky, so I'll be like explaining this through, but please stop this video at this point and try to solve this problem on your own. In case you are stuck at some point, or you want you're not understanding this problem, please feel free to reach out to me at any point of time. So first step is to calculate the value of IN. So replace 1 ohm resistor. So 1 ohm resistor is at this point by short circuit. So I will be replacing it in that point, and then I'll be writing the equivalent circuit in this form. One of the most important step that is to be noted is that you have to draw equivalent circuit in each and every case, because it gives you an analytical vision of how we can approach a particular problem. So that's the reason why we're doing that. So by source transformation, we will be applying source transformation at this point, because 1 amp is connected in parallel with 3 ohms. So V is equal to IR 1 into 3, that is 3-volt source will be connected in series by applying source transformation here. So the source transformation concept with problems is also explained in our previous video. In case you have any doubts with respect to it, please do refer to it. I will be providing the link in the description. So over here you have the voltage source. Be very careful, current is in downward direction, that is why the voltage source is also inverted, that is given as minus and plus in this way. I'll be indicating the direction as the current enters, it will be plus, and when it leaves minus. Write it with respect to each and every component, because you'll not go wrong. We will be applying KVL to mesh 1. We'll be indicating the signs as shown. So with respect to mesh 1, we can write it as minus 3 volt, because it is living at minus 3. And once it is done, we have minus 3 I1, because with respect to the current I1, and with respect to 3 ohm resistor, it is entering at plus and leaving at minus. So we'll be having minus 3 I1, and again minus 2 into I1 minus I3. So because it is entering at plus and leaving at minus, minus 2 is the value of resistor, I1 minus I3, because I3 is in the opposite direction with respect to I1. So that is equal, like, and then you also have a 1 volt uh, voltage source that is there. So from minus to plus, it is equal to plus, so plus 1, you'll be equating it to 0. You'll be simplifying this equation, you'll be arriving at one equation. This is equation number 1, this can be labeled as equation number 1. Again applying KVL to mesh number 2, that is with respect to this mesh. If you carefully observe, I'll be applying it from this end, that is nothing but minus 1 volt. So when it is living at minus 1 volt, you'll be writing it as minus 1, and once it is done, it will come across this particular resistance branch. So minus 2 ohms, because it is living at minus 2 with respect to 2 ohm resistor. I2 minus I3, because I3 is in the opposite direction with respect to I2. So again minus 2 into 2 times I2, because with respect to minus 2 ohms, it is living at minus 2. So you'll be writing minus 2 I2, that is equal to 0. Once simplifying this, you'll be arriving at another equation that is written over here. So next step is to apply KVL to mesh 3. So be very careful with respect to this. I've indicated plus negative, but with respect to I3, it is in the opposite direction, and it will, the plus and negative will be in this particular direction. So you will be getting it like this. So apply KVL to mesh 3, you'll be getting minus 2 into I3 minus I1, that is with respect to minus 2 ohms. It is living at minus terminal, and 2 ohms is the value of resistor. I3 minus I1 is in the opposite direction, I'll be writing it that way. Again minus 2 ohms is entering with respect to 2 ohm resistor here, and 2 ohm is the value. So 2 into I3 minus I2, because I2 is in the opposite direction with respect to I3. So it is equated to 0 according to the algebraic sum of EMFs in a closed loop is equal to 0, KVL law. So once that is done, I'll be finding another equation, that this will be the third equation with respect to our problem. Solving all these three equations simultaneously, we can arrive at the values of I1, I2 and I3. But looking at the circuit, I3 is the current flowing with respect to, if you are if they've asked us to find the value of IN. IN is nothing but the current flowing through IN. This branch is nothing but I3. So you'll be writing it as I3 is equal to IN is equal to minus 0.59 amps. So once you are clear with this particular concept, once you are finding out the value of IN, our next step is to calculate the value of RN. That can be done by replacing voltage source by a short circuit and current source by an open circuit. So looking at this from this particular branch terminals, that is the resistance elements, the current and voltage sources are represented by their internal resistance. So we can simplify this in this manner, because looking at this, 2 ohms and 3 ohms are connected in parallel, because they are connected between the same 2 points, that is at this point and this point. Similarly, 2 ohm and 2 ohm are connected in parallel, because they are connected between the same 2 points, that is here. So with respect to this point and this point. So we'll be writing it in this form of representation. 2 ohm and 3 ohm are in parallel. We'll be applying parallel theorem, like parallel connection combination formula, that is 2 into 3 by 2 plus 3. And again 2 ohm and 2 ohm are connected in parallel. We'll be simplifying that. You'll be getting 1 ohm. So these are in series combination. Rn can be found out by adding these two. You'll be getting 2.2 ohms. So calculation of IL, how can that be done? You'll be representing it Norton's equivalent circuit, and now they've asked us to find the value of IL. So we know by current divider rule, this is the formula. So in order to find the value of IL, we have 0.59, that is the main current that is flowing, into 2.2 ohms, that is 2.2 ohms is the parallel resistance branch with respect to 1 ohm, and 2.2 plus 1, that is sum of resistances, that is equal to 0.41 amps. So this is how you will be solving problems related to Norton's theorem, standard 3 steps that you have to follow, and solve using normal KVL, KCL, current divider rule, source transformation, or mesh analysis with respect to supernode and supermesh. You have a lot of concepts with respect to it. So that's it for this video. If you like this video, please do like it and subscribe to our channel for regular updates. If you have any questions, please feel free to reach out to me by typing in your questions in the comment section below. Thanks for watching this video. Please do subscribe it.